Hello everyone, Dr. Chen here. Uh, we're going to review a special example which is called a spectrometer. We use magnetic field and the electric field together to identify the particles, which is application in chemistry. So first, let's review the magnetic force. So in Mathematica, the best way to calculate the mathematical force is you need to find the charge, velocity of the charge, magnetic field, and rigorously in vector notation, the magnetic force is equal to Q multiply vector product of V, velocity of the particle, and B, the magnetic field. Of course, we say we have a way to calculate the magnitude of magnetic force as Q V B sine phi, and this phi is the angle between V and B. If you have your V, you have your B, and the angle between them is phi, and the magnitude is given by QVB phi, and then the direction of the force is given by right-hand rule. So if you need to refresh what is right-hand rule, I suggest you go to the previous video I recorded, magnetic force. This is magnetic force, magnitude, QVB sine phi, and direction, right-hand rule. And there's another concept of force called Lorentz force. So basically, Lorentz force is electric force and magnetic force for a charged particle moving inside the electromagnetic field. So you can see this part is electric force, and this part QVB is the magnetic force. So if you add electric field and the electric force and the magnetic force on a moving charged particle, it gives us the Lorentz force. Now we can engineer a device that only allow particular velocity of particle passing through this device. So we call it a velocity selector. So we want the charged particle to go through this device and deflect it. So what's the requirement? First, I think we need to figure out what's the direction of electric force and the magnetic force on this charged particle when it's moving through this device. Electric field is pretty simple. Electric field for a positive charged particle, you put a positive charged particle inside the electric field. The electric force would be in the same direction of electric field. Now in this problem we have electric field is pointing down, so our electric force should also be pointing down. And then we need to use right-hand rule to find out what's the magnetic force. So velocity is pointing in this direction, and for the cross magnetic pointing into the screen, right-hand rule give us magnetic force pointing up. So magnetic force and the electric force is pointing in the opposite direction. And we want the particle to move and deflect it through this device, through this velocity selector device. So how can the charged particle move and deflect it? Which means there's no acceleration in the y direction. So A has to be 0 in the y direction. If there is acceleration in the y direction, the particle is going to move and either being bumped into the positive plate or negative plate. So the requirement is acceleration zero. Now we need to go back to Newton's first law. How can we have acceleration zero? We need net force to be zero, right? So what are the forces acting on the charged particle? We have electric force, Fe, and then we have magnetic force, Fb, in the opposite direction. So as long as those two forces have the same magnitude, opposite direction, they will add up to zero. The net force would be zero, acceleration zero, and the particle will coming out deflected. So we find out the criteria. Electric force has to equal magnetic force. Magnitude of electric force, the equation is charge times electric field, Q times E. Magnitude of magnetic force, QVB sine phi, phi is the angle between velocity and B. If for us, V is pointing in this direction and B is pointing into the screen, and V is in the screen, so apparently they have 90-degree angle between V and B. So sine 90 degree give us 1. We get QE equals QVB, and then we can cancel the Q on both sides. We have E equals V over B. We find out for velocity selector, it will select particles with velocity E over B. And we can plug in the unit for E and B. We will find out E over B indeed give us a quantity has dimension velocity. Now we select velocity v, the particle with velocity v, we have this particle enter another magnetic field. Now this time B2 doesn't necessarily has to be equal to B1. And as we said, the magnetic force here would be pointing up. But if your initial velocity is exactly perpendicular to the magnetic field, the particle would go a circular trajectory, because for all the time the magnetic force is perpendicular to the instantaneous velocity, so perpendicular to the trajectory, so this particle give us a uniform circular motion. And we should have Fb equals to m times acceleration of the particle, and acceleration is v squared over r. So if we can find out what is Fb, we can calculate what would be the, how to relate m and r with the measured r and the m and the q of the charged particle. So let's try to derive this equation. So this is magnetic force for the particle in region 2 with magnetic field B2. So the magnitude of magnetic force is QV B2 sine 90 degree, because we still have angle between velocity and the B 90 degree here. V always perpendicular to B2, where we have this 90 degree. Magnetic force left hand side should equals to m times a, and a is centripetal acceleration equals v squared over r. So I can solve for m from this equation. I find m is q b2 r, and v, which we already know after you select this particle through this velocity selector. Now, of course, we can replace v equals e over b1 that we have for the velocity selector and have an expression for m. But this one is already pretty useful. So this is a theoretical duration. So let's apply this equation to an example. So we have a synchrony iron, which means you have atom and then you strip one electron away. So this ionized atom would carry one electron charge of electric charge, but it's positive, right? Because if you remove an electron, you remove a negative charge, the atom would carry a net positive charge with 1.6 10 to the negative 19 coulomb. And we accelerate an other particle going through a velocity selector, so only particular velocity of particles would passing through the velocity selector, and the velocity selector has electric field 155, has magnetic field 0.0315 T, and then those particle with velocity v enters another region with b2 0.0175 Tesla, and then this radius is 17.5 centimeter. We want to know what is mass of this iron. Okay, so that's a question. So let's solve the velocity. What's the velocity of the particle after the velocity selector? So the criteria as we discussed, it has to be FB equals to FE, and FB is QVB sin 90 degree equals QE. So V sin 90 degree is 1, and Q and Q cancel each other, so my V has to be E over V1. Plug in all the numbers. I should have I should have 4,920.6 meters per second. Okay, so that's the particle going through region 2 here. And we measured this radius. We want to find out the mass. And I know what is P2. So we have the magnetic force at region 2, QVB2 sin 90 degree, which is a magnetic force in region B2, equals to mv squared over r, and v already solved from question A. V and V can cancel. Sin 90 degree give me 1. So m equals q b2r over v. Now I just need to plug in all the numbers. Q is 1.6 10 to the negative 19. B is 0.0175. R is 0.175 meter. V is 4920.6 meter per second. Everything together, I find the mass of this iron is roughly 10 times 10 to the negative 26 kilogram. So now you can identify what kind of particle it might be, which particle has 10, roughly 10 times 10 to the negative 26 kilogram. Hope this example would be helpful for you to solve problem on your exam. And I will see you next time.